Good day, I'm Christine F. Reyes and my report is about security in network, threats in network, and network security controls. Let's discuss first the threats in network. Threats in network. Main aims of threats are to compromise confidentiality, integrity applied against data, software, hardware by nature accidents, and non-malicious humans and malicious attackers. There are different topics under threats in network. Let's proceed with what makes a network vulnerable. What makes a network vulnerable? It is because of anonymity, many points of attack, sharing, and complexity of system. What is anonymity? An attacker can mount an attack from thousands of miles away and never come into direct contact with the system, its administrator, or users. The potential attacker is thus safe behind an electronic shield. The attack can be passed through many other hosts in an effort to disguise the attack's origin. Next is the many points of attack. An attack can come from any host to any host, so that a large network offers many points of vulnerability. Next is sharing. Because networks enable resource and workload sharing, more users have the potential to access network system than on single computers. Last is the complexity of system. What is complexity of system? The attacker can use this power to advantage by causing the victim's computer to perform part of the attack's computation. And because an average computer is so powerful, most users do not know what their computers are really doing at any moment. Threat precursors. A precursor indicates that an incident may occur in the future. Precursors allow security professionals to anticipate a possible forthcoming attack and tighten protection measures accordingly. These are the attacks that is under threat precursors. Number 1 is the port scan. It is an easy way to gather network information. It is to use a port scan, a program that, for a particular IP address, reports which ports respond to message and which of several known vulnerabilities seem to be present. Port scanning tells an attacker three things: which standard ports or services are running and responding on the target system. Second is what operating system is installed on the target system. And last, what application and versions of applications are present. Next is the social engineering. The point of social engineering is to persuade the victim to be helpful. Social engineering involves using social skills and personal interaction to get someone to reveal security-relevant information and perhaps even to do something that permits an attack. Next is the reconnaissance. It is the general term of collecting information. In security, it often refers to gathering discrete bits of information from various sources and then putting them together like pieces of puzzle. Next is the operating system and application fingerprinting. It describes the method of utilizing gathered information of a target host to find out what application server, web server, or operating system the machine is running on. In other words, fingerprinting is the process of identifying a remote host operating system or application or web server by probing that host and analyzing replies from it. Next is the bulletin boards and chats. Numerous underground bulletin boards and chat rooms support exchange of information. Attackers can post their latest exploits and techniques, read what others have done, and search for additional information on systems, applications, or sites. Remember that, as with everything on the internet, anyone can post anything, so there is no guarantee that the information is reliable or accurate. Next is the availability of documentation. The vendors themselves sometimes distribute information that is useful to an attacker. For example, Microsoft produces a resource kit by which application vendor can investigate a Microsoft product in order to develop compatible complementary applications. This toolkit also gives the attacker tools to use in investigating a product that can subsequently be the target of an attack. We study the precursors to an attack so that if we can recognize characteristic behavior, we may be able to block the attack before it is launched. Next is threats in transit, eavesdropping and wiretapping. The term eavesdrop implies overhearing without expending any extra effort. For example, we can say that an attacker is eavesdropping by monitoring all traffic passing through a node. The more hostile term is wiretap, which means intercepting communication through some effort. The choices of wiretapping are cable, microwave signals, satellite communications, optical fiber, and wireless network. Next is the protocol flaws. Each protocol is identified by its request for comment number. In TCP, the sequence number of the client increments regularly, which can be easily guessed, and also which will be the next number. Suppose someone can guess a client's next sequence number. That person could impersonate the client in an interchange. Sequence numbers are incremented regularly, so it can be easy to predict the next number. Next is the impersonation. Impersonation is a more significant threat in a wide area network than in a local one. Also, impersonation attacks should not be ignored even on local area networks, because local area networks are sometimes attached to wider area networks without anyone's first thinking through the security implications. In an impersonation, an attacker has several choices. Firstly, guess the identity and authentication details of the target. Pick up the identity and authentication details of the target from a previous communication or from wiretapping. Next is the circumvent or disable the authentication mechanism at the target's computer. Use a target that will not be authenticated. And last is the use a target whose authentication data are known. Spoofing, guessing or otherwise obtaining the network authentication credentials of an entity permits an attacker to create a full communication under the entity's identity. Examples of spoofing are masquerading, session hijacking, and man-in-the-middle attacks. First is the masquerading. In a masquerade, one host pretends to be another. A common example is URL confusion. Domain names can easily be confused, or someone can easily mistype certain names. Thus, xyz.com, xyz.org, and xyz.net might be three different organizations. Names with or without hyphens, such as coca-cola.com versus coca-cola.com. Next is the session hijacking. Session hijacking is intercepting and carrying on session begun by another entity. For example, using Telnet, if a system administrator logs in remotely to a privileged account, a session hijack utility could intrude in the communication and pass commands as if they came from the administrator. Next is the man-in-the-middle attacks. A man-in-the-middle attack is a similar form of attack in which one entity could intrude between two others. This picture shows the normal flow versus the man-in-the-middle flow, wherein we can see that in the normal flow, it is just the client and the server only. However, in the man-in-the-middle flow, there is someone between the client and the server. That's why it is called man-in-the-middle. Next is the message confidentiality threats. An attacker can easily violate message confidentiality because of the public nature of networks. Eavesdropping and impersonation attacks can lead to a confidentiality or integrity failure. Here we consider several other vulnerabilities that can affect confidentiality. First is the misdelivery. Sometimes, messages are misdelivered because of some flaw in the network hardware or software. Second is the exposure. Along the way, the content of a message may be exposed in temporary buffers, at switches, routers, gateways, and intermediate hosts throughout the network, and in the workspaces of processes that build, format, and present the message. Furthermore, a malicious attacker can use any of this exposure as part of a general or focused attack on message confidentiality. Last is the traffic flow analysis. Sometimes, not only is the message itself sensitive, but the fact that a message exists is also sensitive. We need to protect both the content of messages and the information that identifies sender and receiver. Message integrity threats. In many cases, the integrity or correctness of a communication is at least as important as its confidentiality. In fact, for some situations such as passing authentication data, the integrity of communication is paramount. In other cases, the need for integrity is less obvious. We consider threats based on failures of integrity in communication, falsification of messages. An attacker can take advantage of our trust in messages to mislead us. Next is noise. Such unintentional interference is called noise. These forms of noise are inevitable, and they can threaten the integrity of the data in message. Next is the website defacement. One of the most widely known attacks is the website defacement attack. Because of the large number of sites that have been defaced and the visibility of the results, the attacks are often reported in the popular press. Website vulnerabilities attacks are known as buffer overflows, and address problems, application code errors, and last is the server-side include problems. Denial of service. A denial of service attack is an attack meant to shut down a machine or network, making it inaccessible to its intended users. Denial of service attacks accomplish this by flooding the target with traffic, or sending it information that triggers a crash. Denial of service attacks. First is the transmission failure. Communication fail for many reasons. From a malicious standpoint, you can see that anyone who can sever, interrupt, or overload capacity that you can deny their service. Next is the connection flooding. The most primitive denial of service attack is flooding a connection. If an attacker sends you as much as data as your communication system can handle, you are prevented from receiving any other data. Next is the echo Trojan. This attack works between two hosts. Trojan is a protocol that generates stream packets. It is used to test the network's capacity. Next is the ping of death. A ping of death is a simple attack. Since ping requires the recipient to respond to the ping request, all the attacker needs to do is send a flood of pings to the intended victim. Example, the attacker on a 100 MB connection can easily flood a 10 MB victim. The ping packets will saturate the victim's bandwidth. Number 5. Smurf. The Smurf attack is a variation of a ping attack. It uses the same vehicle, a ping packet with two extra twists. Number 6. SYN flood. Another popular denial of service attack is SYN flood. This attack uses the TCP protocol suite, making the session-oriented nature of this protocol work against the victim. Number 7. Traffic redirection. A router is a device that forwards traffic on its way through intermediate network between a source host network and a destination. So, if an attacker can corrupt the routing, traffic can disappear. Number 8. DNS attacks. Our final denial of service attack is actually a class of attack based on the concept of domain name server. A domain name server is a table that converts domain names like att.com into network address like 211.217.74.130. This process is called resolving the domain name. For efficiency, it caches the answers it receives so it can resolve that name more rapidly in the future. We are done on the first topic, and the next is the network security controls. Network security controls are used to ensure the confidentiality, integrity, and availability of the network services. These security controls are either technical or administrative safeguards implemented to minimize the security risks. These are the topics under the network security controls. Let's begin with the security threat analysis. Security threat analysis. It is the process to determine which component of the system need to be protected and the types of security risks they should be protected from. I summarize these threats with lists: intercepting data in traffic, accessing programs or data at remote hosts, modifying program or data at remote hosts, modifying data in transit, inserting communications, impersonating a user, inserting a repeat of a previous communication, blocking selected traffic, blocking all traffic, and running a program at a remote host. Why are all these attacks possible? Size, anonymity, ignorance, misunderstanding, complexity, dedication, and programming all contribute, but we have help at hand. We look next at the specific threats and their countermeasures. Design and implementation. Architecture. As with so many of the areas we have studied, planning can be the strongest control. The architecture or design of a network can have a significant effect on its security. The main areas to cover are segmentation, redundancy, and single points of failure. Segmentation. Just as segmentation was a powerful security control in the operating systems, it can limit the potential for harm in a network in two important ways. Number one, segmentation reduces the number of threats. Number two, it limits the amount of damage a single vulnerability can allow. Redundancy. Another key architectural control is redundancy, allowing a function to be performed on more than one node. Last is the single points of failure. One way to evaluate the network's architecture tolerance of failure is to look for single points of failure. That is, we should ask if there is a single point in the network that, if it were to fail, could deny access to all or significant part of the network. Encryption. Encryption is probably the most important and versatile tool for a network security expert, because networks often involve even greater risks. They often secure data with encryption, perhaps in a combination with other controls. There are two types of encryption scheme exists. Number one is the link encryption. In link encryption, data are encrypted just before the system places them on the physical communications link. Link encryption is invisible to the user. The encryption becomes a transmission service performed by a low-level network protocol layer, just like message routing or transmission error detection. Next is the end-to-end encryption. As its name implies, end-to-end encryption provides security from one end of a transmission to the other. The encryption can be applied by a hardware device between the user and the host. Content integrity. Content integrity comes as a bonus with cryptography. No one can change encrypted data in a meaningful way without breaking the encryption. This does not say, however, that encrypted data cannot be modified. Changing even one bit of an encrypted data stream will affect the result after decryption, often in a way that seriously alters the resulting plain text. We need to consider three potential threats. Number one is the malicious modification that changes content in a meaningful way. Malicious or non-malicious modification that changes content in a way that it is not necessarily meaningful. And last is the non-malicious modification that changes content in a way that will not be detected. Strong authentication. Authentication. In the network case, however, authentication may be more difficult to achieve securely because of the possibility of eavesdropping and wiretapping, which are less common in non-network environments. Also, both ends of communication may need to be authenticated to each other. Here are the main issues. Number one is the one-time password. A one-time password can guard against wiretapping and spoofing of a remote host. A one-time password is good for one use only. Next is the challenge response systems. The simplest example of a challenge response protocol is a password authentication, where the challenge is asking for the password and the valid response is the correct password. Last is the digital distributed authentication. It is to authenticate non-human entities in a computing system. Alarms and alerts. The logical view of network protection looks like on figure below, in which both router and the firewall provide layers of protection for the internal network. Honeypots. A honeypot is a security mechanism that creates a virtual trap to lure attackers. A honeypot has no special features. It is just a computer system or a network segment loaded with servers and devices and data. There may be some monitoring capability that is done carefully so that the monitoring is not evident to the attacker.
So you're probably asking yourself, what's a honeypot? Well, first off, there are many security controls within an organization's environment. In this instance, this one has a firewall. Every organization with internet connectivity is likely going to have a firewall in place, which can eliminate a lot of potential threats. But the reality is, hackers still find ways to get into an organization's environment. And although network segmentation can be put into place as well, that doesn't mean it's preventing security threats from gaining access to systems. So what a honeypot is designed to do is replicate a login page, similar to other systems such as finance, IT, business applications, and productivity. Now, when an attacker logs in, from a hacker on the internet who gains access to a corporate environment, or perhaps someone internally who's trying to access one of these systems, the honeypot will detect that activity and immediately send an alert to IT or an IT security team. This now provides visibility to that team, who can determine if someone is doing something malicious within the organization's environment. And that's the value of a honeypot, which is included as part of Blumera's service, a simple and useful way of strengthening your network.
These are my references. That's all for my report. Thank you.